Hello, everyone. My name is Ratisha Kiran, and I will be presenting my assignment, the LM5 assignment today in the data mining and healthcare class. The goal of this assignment was to apply association rule mining techniques to healthcare data and understand how patterns of co-occurring diagnosis can be discovered using both SQL and WETCA. By completing this project, I learned to differentiate between association and classification rules, understand why FP tree is faster than a priori, and measure rule quality through support, confidence, lift, and conviction. And here are some of the assignment objectives that I was able to identify while finishing this assignment. This slide highlights the key differences between association and classification rules. Association rules are usually unsupervised. They find patterns in data without predicting a specific outcome. For example, here, the association rule example would be people with a cough and fever often also just have the flu. They don't really have any context clues or anything. They're just associating that the person has the flu. Classification rules, however, are supervised. They predict a target outcome based on input variables, such as predicting the flu diagnosis from a high temperature and cough. The key difference is that association asks what goes with what, while classification asks what predicts what. This was one of the next questions, and it talks about why FP tree is faster than a priori. So in this slide, I like to explain that a priori repeatedly scans the database for each item set size, which makes it slow, especially with large data sets like ours. FP tree, on the other hand, scans the databases only twice and builds a compressed tree that stores item frequencies. This tree structure eliminates the need to generate candidate item sets, making it much more efficient. For example, in a healthcare context, FP tree can quickly identify patterns like hypertension, hyperlipidemia, and diabetes, which are co-occurring with obesity, without rescanning all patient data multiple times. So the next question was going over the different types of metrics of association, which are used to evaluate the strength of association rules. Support measures how often items occur together. For example, what percentage of patients had both hypertension and diabetes? Confidence shows how likely one condition appears given another. For instance, how many patients with hypertension also have diabetes? So we're able to see what support means. For confidence, it shows how likely one condition appears given another. For instance, how many patients with hypertension also have diabetes? Lift shows how much more likely A and B occur together than by chance. Conviction evaluates dependence and it rule rarely wrong. And it shows how dependent two items are. The higher the conviction, the more reliable the rule. Together, these metrics help us evaluate not only if two conditions co-occur, but how strongly and meaningfully they are related. For the next part of the assignment, we had to use test claims and SQL. And for this assignment, I calculated the support for single diagnosis using the test claims 10K database, which I can show here on switching. Right here. Oh, I think it got paused. So right here, I have create table opened right here. And then I'm using claims 10K, and then these are all of my different types of values here. I was able to create the table diagnosis 10K and then claim 10K. And the first question here helps me show the different type of patients, and it shows the most common co-occurring diagnosis pairs. I was able to get this type of code for question 1. And then for question 2 here, I have this with all of these codes here. And then for question 3 here, I was able to get this code done. Okay, go back here. So support for single diagnosis per patient, I was able to use the data from these two, and I linked the claims code plus a diagnosis table. And these were the most common diagnoses I was able to get from my code. And this is how it outputs the code. And it shows the numeric amount of how many people have this and the percentages that are diagnosed. Chronic conditions dominate the data set, mirrors real-world healthcare trends. The next question asks about item sets with 2 elements and support of at least 0.05. Data analyzed from test claims 10K, patient-level diagnosis pairs. So here it shows the most frequent co-occurring diagnoses that are listed right here. And these are the different types that we have. So these interpret to show hypertension often co-occurs with other chronic conditions, such as diabetes, anemia, vascular, and pulmonary diseases. This reflects common comorbidity patterns in patients with complex chronic illnesses. This was the next question here. All item sets with 3 elements and supports at least 0.05. So for 3 item sets, I looked at triples of diagnosis that appear together in at least 5% of patients. The top combinations include hypertension, diabetes, and anemia, which appeared in 22% of patients. Hypertension was present in almost every top triple, confirming it was a central condition in chronic disease clusters. This suggests a high comorbidity burden involving metabolic and cardiovascular conditions. The next part of the assignment was using the Weka association mining setup and algorithms. And the objective of this was to discover the relationship among diagnosis per patient using association mining. So how I was able to basically convert my CSV, I basically combined the dataset test claims 10K, and then I converted it from a CSV to ARFF format. And then I used string nomial, and then I applied string nomial filter before running algorithms. And then I wanted to run the 2 different algorithms which are a priori and FP growth. And these were the parameters that I used. So I was able to compare the number of rules, rule length, and overall strength. And then I wanted to make sure FP growth evaluated rules using lift and conviction metrics. So my a priori results, when running this data claim, no large item sets were found at 5% support. This happened because the data set was very sparse. Individual claims don't contain many diagnoses. To find meaningful rules, we would need to lower the support threshold or use a per person data set. For my FP growth results, per person data set or lower support. And these were the parameters that were used for that. And the effect of changing support and confidence, I was able to also. This slide demonstrates how adjusting support and confidence thresholds changes the number and strength of rules. Lowering support increases the number of rules, including rare combinations, while raising support limits results to only the strong patterns. Similarly, lowering confidence allows weaker rules, and raising it focuses on highly reliable relationships. For example, at 0.05 support, a priori found about 60 rules, but only at 0.10, only 25 remained, showing the trade-off between quantity and reliability. Frequent item sets. Both a priori and FP growth found the same top frequent item sets: hypertension with diabetes, hypertension with anemia, and the triple hypertension vascular disease diabetes. These findings align with the SQL results and confirm consistent chronic disease clusters across methods. FP growth rule metrics. This slide shows examples of the rule metrics calculated for FP growth. The rule hypertension to diabetes had a support of 0.43, confidence of 0.49, and lift of 1.12, meaning the two conditions occur together 12% more often than by chance. A second rule, hypertension and anemia. Diabetes had a support of 0.22 and lift of 1.08, also indicating a meaningful relationship. These metrics help qualify the clinical significance of each rule. Overall, my summary of WICA findings showed that FP group was faster and more memory efficient than a priori. A priori might have offered more flexibility for exploring thresholds, but it took longer to run overall. FP growth ran faster and used less memory than a priori. Overall, the analysis shows how data mining can uncover meaningful relationships in healthcare data sets. Okay, and that is all I have for today. Thank you.